In the last video, we discussed a very important fact, which is that in the canonical ensemble, we can talk about the distribution, the probability distribution, upon the states of a single particle system before we ever think about having many particles in our system together. And this is very important for a couple of reasons. One is that these single particle systems really can occur sometimes in the laboratory if we're careful enough. And the second is that it gives us some building blocks, I should say, in order to think about how multi-particle systems work. All right, so in this video, we're going to start looking at multi-particle systems, and we're going to do that mainly by way of example. We're going to look once again at the Einstein solid. Remember that this system is composed of distinguishable harmonic oscillators. Let's just say n of them. So n distinguishable harmonic oscillators, HOs. All right, so the states look like N1 through Nn, where n sub k can go from 0 to infinity and is an integer. Good. Okay, so the energy E sub n1 dot 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 n sub n is going to be the sum over k of h bar omega times n sub k plus 1/2. In other words, it's just the sum of the harmonic oscillator energies of each of these capital N harmonic oscillators. Good. Okay, so without further ado, we can find the partition function sub ES for Einstein solid of the Einstein solid. So that is going to be the sum over states, we'll get to that in a second, of e to the minus this energy. So, or e to the minus beta times this energy. So that'll be a sum k h bar omega n sub k plus 1/2. Excellent. So this sum is actually a set of nested sums. In fact, there will be capital N nested sums, but we can write them all with one summation symbol. So I'm just going to write the sum over n1 up to n capital N, and each of these can run from 0 to infinity. Good. All right, so the next thing that I want to do is look at the fact that because this is e to the power of a sum, so there's a sum in the exponent, we can break this up into a product of exponentials. So we're going to have our sum over all of these values, n sub n, of the product, k goes from 1 to capital N, of e to the minus beta h bar omega n sub k plus 1/2. Now, there's something very important about what we've just done. In particular, our ability to break this into a product of exponentials is really going to help us down the road. And let's think about why we could do that. It's because the Hamiltonian was able to, sorry, not the Hamiltonian, in this case, just the energy, was able to be written as a sum over these indices, where each term in the sum depended only on its own index. Good. That turns out to be the case exactly when we have a non-interacting theory. So the key is that these harmonic oscillators are not interacting with each other. Each one is just independently doing its own thing. If we had, for instance, a bunch of electrons in a box and we tried to model the Coulomb repulsion between the electrons, we would see that the sums would include mutual pairs of positions of electrons. And that would break our ability to express things into a product over these sorts of individual variables. So this is a very nice form. And it's a very nice form for the following reason. We can, in fact, swap the order of the product and the sum here in a careful way. So what's happening here is that we have a bunch of terms multiplied together, or a bunch of factors multiplied together, and then we're going to sum over every possible value that they could take. Now, I want to work out on the side here a little example of something like this as well. So let's imagine that we just have three quantities, A, B, and C. And A, B, and C can all take on three different values, let's say. So A1, A2, A3, B1, B2, B3, C1, C2, C3. Good. So let's write, we want to look at, so just an example, look at A, B, C, and then we'll look at the sum over all these different values we can take. So we get A1. Actually, to make our lives a little bit easier, say that they can each take on two values. So we'll get A1, B1, C1. That'll be the first term in our sum, plus A1, B1, C2, plus A1, B2, C1, plus A1, B2, C2, plus so now we've looked at all the A1 terms, A2, B1, C1, plus A2, B1, C2, plus A2, B2, C1, plus A2, B2, C2. Good, 8 terms. Okay, so this would be like what we've exactly expressed here. Now, let's conversely look at the product A1 plus A2 times times B1 plus B2 times C1 plus C2. Notice that this has an expansion which is exactly the same. So for instance, if we take the first one each time, we get this term. If we take A1 and then B2 and then C2, that's this term. If we take A2, B1, C2, that's A2, B1, C2, we get that term. And so on and so forth. This product of sums is exactly the same as this sum of products. So let me write that here in exactly the way that we have it here. This becomes a product, k goes from 1 to n, of the sum over nk, which now I'll explicitly write is the sum from nk goes from 0 to infinity, of exactly what we had here, e to the minus beta h bar omega nk plus 1/2. But check it out. This is exactly the partition function for the harmonic oscillator that we discussed in the last video. Great. So now we see why these single particle partition functions are actually important in our broader theory. So let's bring this back up here. The Einstein solids partition function is exactly the product from k goes from 1 to n of the single particle harmonic oscillator partition function. But look, this doesn't depend on k in any way at all. So that implies that the partition function for the Einstein solid is exactly the partition function for the harmonic oscillator raised to the nth power. Great. Now I made a note in the last video that the free energy for the harmonic oscillator was not extensive because we only had one particle. But now, given this relationship, we'll see that the free energy for the Einstein solid is extensive. That's because the free energy for the Einstein solid, which is minus 1 over beta times the log of ZES, is equal to minus 1 over beta times the log of ZHO to the nth power. But then the n can just come down. So this becomes minus n over beta times the log of ZHO. And look, this is exactly n times FHO. In other words, in this case, because the particles were not interacting, the free energy for the Einstein solid is just capital N times the free energy for the harmonic oscillator. Okay, so the big upshots of this video are that in the canonical ensemble, we can get nice expressions for the partition functions and free energies of multi-particle systems if those multi-particle systems are not interacting. If the systems are interacting, then we're stuck and we'll need to use different processes to get these partition functions. But this is one case in which we get a very nice result, and one that depends on the single particle physics that we already discussed in the last video. In the next video, we're going to look at the fact that there are, in fact, many different ensembles that we could look at, and each one helps us to get a different free energy. I'm excited to show you that one, and I'll see you then.